In this example, we have to find the two square roots of the given complex number -1 plus I radical 3. So the first thing to do is to express this complex number in trigonometric form. So how do you do that? Notice that when we're talking about a complex number, x plus yi, the trigonometric form will be essentially equal to r times cosine of theta plus I sine of theta. So r in this case will be the modulus of the complex number. Now z is typically equal to this. Okay, so r is the modulus of z and theta is the argument of z. So recall that this point corresponds to the geometric point -1 comma root 3. Okay, so in the complex plane you would find this point. This would correspond to a point being plotted in the complex plane, and the corresponding point in the Cartesian coordinate system is -1 comma radical 3. So as you can see, this will be quadrant 2. Simply because the x value is -1 and the y value is radical 3. Okay, so it's quadrant 2. So now that we know that, how do we determine the r? Recall that the r from the previous videos was equal to the square root of the x squared plus y squared. Okay, so in this case, let's calculate that. This is going to be -1 squared plus radical 3 being squared. So this is equal to 1 plus 4, which is 1 plus 3, which is equal to square root of 4, which is 2. Right? So this is equal to 2. So now we can say that -1 plus radical 3 I is equal to 2, and then we need to find the theta. Now, as we mentioned before, this point is in quadrant 2, and to find the angle theta, you just have to find the arctangent of the quotient of y and x. Okay? Y is equal to radical 3, x is equal to -1, so radical 3 over -1. And then you can express it as radical 3 over 2 divided by -1 over 2, because that's possible. And you know this means that you need to find the angle whose sine is radical 3 over 2. Okay. And you need to find the cosine, the angle whose cosine is -1/2. Right, and we know the angle for that is definitely going to be 2 pi over 3. Because we know that sine of 2 pi over 3 in quadrant 2 is radical 3 over 2, it's positive. And the negative for the cosine is cosine of 2 pi over 3. That's going to be -1/2. Right, so we found the argument of the complex number z, right, the theta. So that means we need to do cosine of 2 pi over 3 plus I sine of 2 pi over 3. Okay, here's how we can express the current complex number. Okay, this complex number can be written as square root 2 squared. Okay, and then cosine of 2 over 2 times 2 pi over 3 plus 2 pi k plus I sine 2 over 2, 2 pi over 3 plus 2 pi k. Okay, and let me separate this. So, and this will lead to what? This will lead to radical 2 cosine of 2 pi over 3 plus 2 pi k being divided by 2 plus I sine 2 pi over 3 plus 2 pi k over 2. Okay, we're going to square this whole thing. So what that does, I'm going to explain to you what happened. So square root 2 was squared, so it gave us the 2, as you can see. This 2 over 2, that did not change anything because 2 over 2 was still 1 multiplying this angle. Same thing for the sine. And adding the 2 pi k, as long as k is going to be greater than or equal to 0, k an integer, right, non-negative integer, as long as this is true, the cosine of the angle will not change, right? Because we know that multiples of 2 pi added to an angle is not going to change the cosine and is not going to change the sine. You might ask, why do we need that? We need that because we're going to need different k values for the sake of having unique square roots, right? Because we want more than one. We want 2 square roots. For this reason, we're going to use k value of 0 and k value of 1. Now the next step from this to this, the 2, as you can see, the 2 here disappeared. The 2 that was there before, the denominator 2 remained. And the reason why 2 disappeared is because of the DeMoivre's theorem, as you can see. Okay? DeMoivre's theorem says that the square here, okay, when you apply it to the individual, to the modulus here, radical 2 in this case, if you apply it to the modulus radical 2, you will square it, it will become a 2, the old modulus that we had for the complex number. If you apply the square to these two terms, then you're essentially applying the n value of 2 here, right, for the coefficient of the theta, of the argument, of the complex number, in both sines and cosines, right? So you would get rid of the square and you would apply it here, right? And if you apply it there, you multiply this whole numerator by 2, this 2 would cancel out with the bottom 2, and therefore we would have had the previous step, right? Because 2 over 2 is 1, and we would have this, okay, as you can see. And again, this whole thing is the argument. Don't be confused. So this whole thing is an argument depending on the value of k, right? So when k is equal to 0, it will be an argument. When k is equal to 1, it will be a different argument, right? It will constitute 2 different square roots by having different values of k, k being an integer greater than or equal to 0, non-negative. The square root can be expressed as radical 2 cosine of 2 pi over 3 plus 2 pi k being divided by 2 plus I sine of 2 pi over 3 plus 2 pi k being divided by 2. Okay? This is already a square root, right? This is square root. This is the expression that you're going to use to find your individual square roots, right? We need 2 of them, but you're going to need it for both. Depending on the k value, you will start from the k value of 0 and 1, and that will be 2 square roots. Why is it a square root? Because before, this whole thing was squared. If you square root it, you will get rid of the square, and you will just have this. So this is a square root expression. So how do you find individual square roots? You might say where k is equal to 0, k is equal to 1, right? So there are 2 square roots with different k values. So the square roots, the first square root is going to be applying the k value of 0. So we're going to get radical 2 cosine of 2 pi over 6. Right, so I'm using the k value of 0. This whole thing is 0. and 2 over 2 cancels out, so I might as well just write pi over 3. That would be easier. Pi over 3, using the k value 0, plus I sine of pi over 3. Right, so this is the first square root. And keep in mind that we have to find the square root in the rectangular standard form, right? So we can't leave it like this. So this result is what? Cosine of pi over 3 is going to be 1/2, and then sine of pi over 3 is going to be what? Radical 2 over 2, right? So as a result, this is equal to what? Radical 2 over 2 plus radical 6 over 2i, right? So this is the first square root that we found. The second square root with subscript 1 is going to be applying the k value of 1 this time, right? We tested the 0, now we're going to plug in the 1. So that's going to be radical 2 cosine. And let's see, so k is equal to 1 will essentially, by the way, we can factor out the 2's, right? So we will have pi over 3 plus pi k. So basically when k is equal to 1, pi over 3 plus pi, right? So cosine of pi over 3 plus pi, that's the result we get, plus I sine of pi over 3 plus pi. Okay, so that's what we get, and as a result, this is equal to what? This is equal to cosine of 4 pi over 3, right? So cosine of 4 pi over 3 plus I sine of 4 pi over 3. So this result is what? This result is radical 2 being multiplied by negative 1/2, and then minus, because sine of pi over 3 is minus radical 3 over 2, so minus radical 3 over 2i. So this is indeed equal to minus radical 2 over 2 minus radical 6 over 2i. Now that we have these individual square roots, the beautiful thing about this is that if you square any of these two, if you square this one, you should get the original complex number that we started with, right? That's the whole purpose of finding the square roots, right? We found unique square roots. However, it's so beautiful that if you square each one of them, you will get the initial complex number that we started with. Let's demonstrate that. So checking, we're going to check this just for fun. If you square the first one, the first square root, you're essentially multiplying it by itself. So you will get, the first product is just basically 2 over 4. The second and third products are the same, so we're going to multiply that by 2, the products. So that will 6 times 2, so radical 12 over 4. And then the final product is radical 6 times radical 6, so that's just 6 over 4i squared. Okay? And what this is equal to is, this thing is negative 1, I squared, so it's minus 6 over 4. 2 over 4 minus 6 over 4 is minus 4 over 4. And then the middle guy becomes what? 4 times 3 inside the radical. Square root of 4 is 2. 2 times 2 is 4. So 4 radical 3 over 4. That's what we get. Right? So as a result, look what happens. This and also there's an I. I forgot to include an I there. So as a result, this is what happens. The 4's get cancelled out. This becomes a negative 1. So as a result, look what happens. Minus 1 plus radical 3i. The same as we started with. Right? Don't worry about the order. I times radical 3 is the same thing as radical 3 times I. Now if we square the second one just for fun, you will get the same thing. Minus radical 2 over 2 minus radical 6 over 2i. Multiplied to itself, and this is going to be the checking, so we're going to separate it from the main work. So this becomes minus radical 2 over 2 minus radical 6 over 2i. So this is what the products are. Just like in the first product, the two minuses give you a plus, so it's going to be 2 over 4. And this is going to be twice the product, which is going to be positive, right? Because both products give you a positive net sign, this one and that one, and this one and this one, right? So twice radical 12 over 4i. Yeah, I'm not going to forget the I this time. Plus, now plus because the two minuses give you a plus. Radical 6 times radical 6, right? So 6 divided by 4i squared. So as you can see, this is just like this line here. So it should give you the same answer, negative 1 plus radical 3i. So this is very, as you can see, this is beautiful. You find the square roots of the original complex number, and then if you check it, if you square each square root, even though they look unique, they're different, they will give you the original complex number. Okay, so I hope this was useful. Thanks so much for watching, and I'll see you in the next video.